Hello friends, I'm back again with a new video in the series TSN Algo for competitive programming. The problem that we'll be solving today is find the kth smallest element in a row and column wise sorted matrix. So if you are given a matrix that is sorted in ascending order, both row wise and column wise, we have to basically find the kth smallest element in the matrix. Here we can assume that k is always a valid number. Let's first consider these examples for understanding the problem statement better. This is a sample input matrix and we have to find the 8th smallest element in this matrix. Okay, this matrix has a total of 9 elements and we have to find the 8th smallest. So you can see it here that 15th is the largest, so the 8th smallest will be 13. So your answer in this case should be 13. Now let's consider this second example. Here we have to find the 13th smallest element in this matrix. Okay, so the answer here is 9. Okay, and if you count the number of elements smaller than 9, it would exactly be 12. Okay, because this is the 13th smallest element, and as you can see that there are 4 elements smaller than this in the first row, then in the second row again 4 elements, and then in the third row 2 elements are smaller than this 9 value, and then in the fourth row it is again 2. So 2 plus 2 plus 4 plus 4, which is 12, and this is the 13th smallest. Okay, let's now talk about the approach that we'll be using to solve this problem. The approach that I'll be discussing today is the one that uses priority queue or min heap, and I'll create a separate video solving the same problem with binary search approach. Okay, but today we'll be focusing mainly on this priority queue or min heap approach. In this priority queue approach, the size of your queue will be equal to min of k and n. Okay, so if k is smaller than n, size of your queue will be equal to k, and if n is smaller than k, size of your queue will be equal to n. Okay, and you can easily correlate this with example. So if you have to find the second smallest element, right, in that case, if you do this comparison, right, so you have to find the second smallest element, right? So your k is 2 whereas your n is 4. Okay, the number of columns are 4. So in that case the size of your queue will be equal to 2. Okay, because you have to find the second smallest, and in that case you don't need to store the other elements in the row. Okay, whereas if you have to find say 10th smallest, okay, then basically your k actually becomes larger than n. In that case the size of your queue will be equal to 4, the number of columns in your matrix. Okay, let me try to elaborate this priority queue approach with the help of an example. Suppose we have to find the kth smallest element in this matrix where k is greater than n. In that case, the size of your queue will be equal to n. Okay, as already described in the previous section. Now, in the first step, we'll add all the elements in the first row of our matrix into the queue. Okay, so in the first step, the elements in our queue will be 1, 2, 3 and 5, which are same as the elements in the first row of our matrix. Then we basically remove the element from the head of our queue. Okay, and we add element below that element below the head element into the queue. So if we remove 1 from the queue, we'll basically add element below 1 into the queue. So we have added 4. Then in the next step, we'll basically remove 2 from the queue and we'll add element below 2 into our queue. Okay, so we have again added 4. Now in the next step, we'll basically remove 3 from the head of the queue and we'll again add 4 into our queue. So now after 4 steps, the elements in our queue are 4, 4, 4 and 5. We'll repeat these steps till our count becomes equal to k, and then we'll return the value present at the head of this queue. For this approach to work, the priority queue should arrange elements in such a way that whenever we are doing a remove operation on the queue, we should always get the smallest element. Now let's jump into the code. I've created this class kth smallest element finder. It contains a main method which contains sample arrays against which we'll be testing our code. The main job here is to implement this kth smallest method. The thing that we have to remember here is that whenever we remove an element from the queue, we have to add the element below this removed element into the queue. So we have to pick the element in the matrix which was below this removed element and we have to add it to the queue. Okay. For implementing this functionality, I'll create a helper class which is grid element, and it will contain the row index of the element, it will contain the column index of the element, and it will contain the value of the element. Okay, I'll provide a constructor as well. So this grid element will actually help me in identifying which is the element below this element in the matrix. Okay, so I'll create a priority queue. And one more thing that I can do is I can make this grid element comparable. Okay, so the comparison will be done on the basis of just this value attribute. Okay, now my priority queue is ready. So basically it will have grid elements and the grid elements are already comparable, so the elements in the queue will be sorted according to this comparable implementation. Now let me try to add the first row of our matrix into our queue. Okay, so I'll be adding these elements. So the row is 0, the column is I, and the value is matrix 0 and I. Okay, oh, so I have added the first row into my queue. The next step is I'll basically check, or I'll run a loop till there are elements in my queue. Okay, and whenever we remove an element from the queue, we have to also introduce a counter variable which is equal to 0. Okay, now if I remove an element from this queue, so and I'll basically, because I've removed it, I'll increase the counter variable. Okay, and I'll check if count equal to k, right? In that case, I'll basically return element dot val. Otherwise, we'll add the element below this element into the queue. So but here we'll have to check if the row plus 1 is a valid row. Okay, so for that I can actually if element dot row index okay, so and here I'll have to add the value at this index matrix. Or I can, for better readability, what I can do is now I can say if row index plus 1 is less than matrix dot length, and then here also we can say row index plus 1, and here we can use column index. And I can add this grid element into my queue. Okay, and whenever this count is equal to k, we can simply return it, and as we know that k will always be a valid value, so we don't have to check for edge cases. Okay, and this was written in the problem statement. Oh, I have missed it. It should be row index plus 1. Okay, and yeah, we are good to test our code. So if we test it now, so it basically says that the 13th smallest element in this test array 1 is 9, and fifth smallest element in this array 2 is 4. Oh, but I've realized that these two arrays are exactly the same, so I can actually use the same array. Okay, so if I run it again, I should get the same result. So 9 and 4. Okay, now for better understanding, let me first sort this input array and then we can compare our test results. Okay, so if I do something like this, arrays dot as list, and then we pass test array into this, and then we create a stream from it, and we create flat map to int. Okay, and stream to array. Yep, so this will give me a int array. Okay, so result and if I call arrays dot short result, okay, so I can basically say shorted test array is, okay, so let's validate our output. Oh, sorry, I have to say arrays dot toString. So it basically says that 13th smallest element in this array is 9, and if we compare it with the shorted array, we'll see that it is correct. Yep, I validated the first result, and for the second result we are looking for the fifth smallest. So 1 2 3 4 5, so 4 is the fifth smallest element, and if I run it for 3, then the answer should be 3, right? Yes, and if I say 20th, then my answer should be 12. Yes, so our output is correct. Today we have seen how we can use priority queue for solving this problem. I'll come up with a separate video on solving this problem using binary search. It is a humble request to all of you to please try these problems on your own first. I'll check in this class in my GitHub repository, and I'll provide a link to my GitHub repository in the description section of this video. I'll also provide a link to the coding portal where you can go and solve this problem. If you like the content of this video, please like and subscribe. If you have any suggestions for me, please write them down in the comment section of this video. Hope to see you soon. Goodbye for now.